Good afternoon, everyone. My name is Xiang Huang, a computer scientist at the Weizmann Center here at University of Wisconsin Madison. Today, I represent our ongoing research on neural time delay, which we call it NeuroTD, a deep learning approach to analyze time delays in neural activities. My presentation has 4 parts. First, I will start with the background. Then I will introduce NeuroTD, framework, simulation study, and 3 applications. Finally, I'll mention ongoing work and acknowledgement. First, what are time delays? What are we looking for? Here, I'm showing 3 types of time delays, and I will apply NeuroTD for each of them. The first one is the left figure shows neuron-to-neuron time delay. The time takes for a signal to pass from one neuron to the other. In application 1, by considering many neurons and the time, like the signal ordering, we're considering like whether we can understand the neural function in like a circuit level, how do they interact with each other. Second, in the middle figure shows like a brain to body time delay. This is easy to understand. The time takes from the signal to travel from between the brain to my body. For example, my brain tells my hand to wave to each other. So in this second application, I will not only compute like the correlation between the brain activity and the behavior activity, but also consider the causality of each of the two. And the third application is considering the with neuron time delay. Here, like we plot like one sweep of patch-seq data. You can see like there's like a time delay between each of those like spikes, and those spikes like delay changes over time. So we consider the dynamic feature of time delay with the neuron and correlate that with the gene expression. So first, how can we get those time delays? We need some environment data, of course. Thanks for recent advance for technologies. Nowadays, we can measure hundreds of neural activity simultaneously with high temporal resolution, something not possible in the past. This table briefly shows some key technology. Casting image, which tracks casting activity in neurons, helps us to monitor neuron firing by visualizing the changes of fluorescent intensity. And both depth electrodes and neural pixels directly measures electrical impulse voltages. While depth electrodes can also measure the 3D position of neurons, a neural pixel can measure hundreds of neurons with high temporal resolution. And in the end, like a patch-seq can measure 3 modality electrophysiological responses, gene expression, and morphology together. Now we have data, we still have 2 main challenges to compute the time delays. First, is due to the high sampling rate data, the variability, like those in casting image and neural pixel, so it's hard to identify key features from those noisy, high sampling rate data. The second challenge is neural and behavior activity exists at a different time scale, different resolutions, temporal resolution, and they may have, it could be like different dynamic features with different shapes. So all those make computing time delay challenging. So to handle those challenges, we propose NeuroTD, which combines deep learning, Siamese neural network, and frequency transformation. Here's how it works. So we'll first take 2 time series data, X and Y, like neural activity and behavior activity. We can see the shape are not matching each other, like the a little difference there. And also we see the 3 passes, which represent 3 events. One to compute like the time shift for each pair of events. So what we do, we first feed them into Siamese neural network. This network processes them into a latent space, where the significant features are extracted to a common shape. Then next, we pull a frequency transformation, such as the short-time Fourier transform, to transform them into frequency domain representation. The key advantage of a frequency transform is like according to Fourier shift theorem, a shift in time domain, which will maybe computed by correlation, is corresponding to linear phase shift in frequency domain, which you can use fast Fourier transform to compute and fast align, and you can apply various constraints to it to make it more robust. And then by comparing the phase difference in the frequency domain of those X and Y, we can directly compute the time delay. As I mentioned in the beginning, there are like 3 events, so the 3 time delay computed. So time delay is not constant, it could change over time. In the first one, it's like 0.2 milliseconds. It's Y minus X, which means Y is like behind X. And the second one is like X lags behind Y. So the computed like time delay is minus 0.2 milliseconds. And the third one is like X happened before Y again. So we'll first perform simulation to validate our method. On the left, we have simulated time varying delay between two signals, red and blue. The Jude-in section highlighted a delay of 1.56 milliseconds in the beginning, and it slowly increased to 3.32 milliseconds in the end. On the right, we compare our model, our method, NeuroTD, with like a classical discrete time warping. You can see like the NeuroTD method, like the blue line follows closely to the ground truth black line, while DTW has struggling to track those changes, and we achieve like 0.16 milliseconds, which is much better than DTW in root mean squared error. Now let's see some real-world application. First, neural circuits in the human brain. On the left, we show the time series data recorded by depth electrodes in human hippocampus. Here, we only show part of the data. We only show 10 milliseconds, although the recording may be hours, but we only show part of them, and we only show 16 neurons. Those neurons, remember, those neurons at a different position of the brain. On the right, we see a heat map showing the time delay between each pair of the 32 neurons computed by NeuroTD. The intensity of the color indicates the magnitude of time delay, ranging from minus 20 milliseconds to 20 milliseconds. From the previous heat map of 32 neuron pairs, we selected 8 neurons that with low alignment or like shift errors. In this figure C, we can see a 3D plot, which will show like plot the real 3D position of those neurons. Remember, we use depth electrodes, so the 3D position of those neurons are available. And then we also compute like the time delay between each pair. For example, from 4 to 6 is 10.2 milliseconds, and the arrow is from 4 to 6, which means like neuron 4 files first, and the neuron 6 follows. So importantly, from the time delay, we can see there's like trend, like the signal is transmitted from neuron 1, 2, then to the ladder layer 3, 5, 4, 5, and then to 6, 7, 8. So this, of course, this is like a small portion of neurons. But imagine if we can measure hundreds, thousands, or millions of neurons, and if we can combine all of those like neurons and those time delay and those small network to a big comprehensive network, then we may be possible to show purely from the time series activity, we can show the collection and how those neurons collaborate together to file one by another to work together. So next we show application 2. The time reveal causality between neurons. I should say may reveal causality between neuron and behaviors in rat brain. On the left, we see neuron activity on the top one. It's neuron activity recorded from neural pixel. And then the bottom is neuron behavior data from like motion capture camera. So this one only shows like one kind of like a motion, like a horizontal movement of the right hand. The right heat map shows time delay between neurons and the behaviors. Here it actually shows the confidence map, like how confident we compute the neuron each pair of like time delays. And using the neuron and the behavior pair with high confidence score, we plot the time varying delay. In this example, and simply only show 2 events, like 2 different events. So at the time 0, the time delay is 0.13 seconds. Remember, like it's y minus x, which means like a behavior happen later and the neuron happen first. So this one suggests like the neuron needs behavior or neuron files before the rat moves. Or there's like strong implication that the neuron activity causes behavior activity. For example, like imagine a scenario, the rat smells very, very good food. And what he do? He would like turn his hand and move towards the food. So this is like the case, like a neuron, the smell, the neuron triggers the movement. At time 150, the delay is minus 0.2 seconds. This means in another case, like the behavior is like happen before the neuron. So this could also imagine a case like, for example, when the rat moves or runs, hit something because like, and then he feel pain. So that means like the behavior happen first, and then the pain or the neuron happen later. So this is a lot of cases. In the last application, I will show how time delay in electrophysiological responses relate to gene expression. So the left figure shows if it's signal during a measurement sweep. We can see the gap between specs changes, and we can compute the feature for this dynamic pattern. So on the right shows we can compute the slope of those, how those gap changes. And we can do this for one neuron, but for one neuron could take multiple measurement. So we have multiple of those sweeps, and we can use a mean or robust mean of this slope as a feature. And here, the higher the feature score, the faster the time delay changes. Next, we compute the correlation score between the gene expression and the effects time delay feature. So this one is the heat map, displays gene expression error across different cells. So that means one column is for one cell, and the gene expression is a vector for this cell. And remember, we compute a feature time delay score for this cell. So we have so we can correlate each gene expression with this feature for all the cells. So on the right, we use a bar chart to show the top 20 genes that have the strongest correlation, positive or negative, with time delay feature. In this way, we identify the genes that are potentially linked to its time delay feature. This is the last figure. So this presents our enrichment analysis result for the top 200 correlated genes, 100 positive correlation and 100 negative correlation. This bar chart highlights some significant gene ontology turn and pathway enrichment along the genes. The key turns including, for example, the sodium ion transport, which below is related to function of effects. This may provide us some insights on how genes and pathways are linked to neural activities. We are currently working on improving the accuracy, robustness, efficiency, experiment validation, and more modality. Just taking 2 examples. For example, currently we only compare X and Y, 2 pairs, a pair of 2 neurons. So it's possible to extend this to a more global optimization to consider more than 2 neurons together as a graph, combined optimization. And secondly, there's a big demand for efficiency. I only showed in that example, I only showed 10 milliseconds of time series data, but for measurement experiments, people doing experiment for hours. Or then that means if 1 second you have 1,000 samples, then that means it's easy to get billions of samples. But most of those times, there's a lot of interesting events. The events are rare. So it's possible we can design a smart way to pre-filter inactive period. In the end, I would like to thank to our lab member at Dr. Wang's lab to UW Medicine, and thanks for NIH and ISF support. And thank you for your attention. And I'm ready for take questions. Thank you.